2x mod 11. What do I mean? I want to draw a picture which helps us to understand what happens when I multiply 2 by anything and I look at the remainder mod 11. In this talk today, I chose 11 because 11 is prime. Things will be different if it's not prime, if we use something that's not prime. But with 11, we can already see some very interesting patterns. If I'm talking about mod 11, what are the possible remainders? Remainders mod 11. I'll draw them almost like a circle, but it's not so important how I'm drawing them because I will change that in a bit. The easiest remainder mod 11 is 0. That's if a number is divisible by 11. You can also have 1 as a remainder. For example, 34 is 1 mod 11 because it's 1 more than 33. Other remainders are 2, 3, 4, 5, 6, 7, 8, 9, and 10. I won't write 11 because I don't need a new remainder called 11. That's already 0. I wrote them around in this circle because that will help us visually recognize patterns. Now, I'm interested in what happens when I multiply 2 times certain numbers and look at the remainder. Let's do a few. Suppose I take 2 times 7. I'm just choosing some random numbers. 2 times 7 is 14. 14, if I want to know what 14 is, mod 11, the remainder is 3. Now I'm going to draw that in this picture by saying, if I started with 7 and multiply by 2, I get 3. My arrow in this picture is the times 2 arrow. So this is doing times 2. Okay, I drew an arrow in this picture. Let's do a few more. Maybe let's try 2 times 5. Well, this is easy mod 11 because it's already less than 11. It's just 10. So now I want to draw an arrow in my picture, which starts from the 5 and goes to the 10. All arrows that I draw are times 2 arrows. Let's do a few more. How about 0? 2 times 0, that's easy, that's 0, mod 11. What kind of arrow is this then? Well, it starts from the 0 and it goes back to the 0. By the way, inside all of this, I'm already holding some information. Some other information that I mean already in this picture is, yes, 2 times 7 is 3, mod 11. But not just 2 times 7, also 2 times 18. 18 and 7 are the same, mod 11. If I already have 2 of the same things, 7 and 18 are the same mod 11, it will be the same thing, mod 11. And just to remind why that's the case, I just want to do a very, very short calculation here. 2 times 18 is just 2 times 11 plus 7. And that's why, since there was already this 11 here, it has the same remainder as 2 times 7 mod 11. So whenever I'm doing my calculations mod 11, I can reduce mod 11 even before I'm done with the calculation and then multiply. And again, I'm emphasizing this 3 bars doesn't mean that that's the remainder. It just means that the difference between the 2 sides, this difference here, this gap, is a multiple of 11. Okay? So actually, each one of these numbers in the circle represents infinitely many numbers. You see this number 9, it's not just 9. It also represents 20. It also represents 31. It even represents -2. These are all the same in this class. That's the term we call them. We call this, if you see certain English words, when you read about number theory, in this, you will see this called as a residue class. Residue is how people think residue as an English word. An English word, residue means what is left over from something. And so it's like the remainder when these are divided by 11. You will also see another word used in English textbooks. It is called congruence class. C-O-N-G-R-U-E-N-C-E. Congruence class. This is because the reason for that word congruence class is because that is how this 3 equal sign is often pronounced. The way you say it when I write 2 times 7, you've noticed I've never said 2 times 7 equals 3 mod 11. The way we always say that 3 equal sign is we say 2 times 7. The way we usually write, the way we usually say something like 2 times 7, 3 bars, 3 mod 11, we usually say in English that 2 times 7 is congruent to 3 modulo 11. So if you ever see this written down, all this means is that. But the reason why you see the word congruence class appear is because that congruent is this. Okay? I'm just sharing this because a lot of lessons, a lot of information about number theory is in many languages. You certainly have many in Chinese. But if you want to look at, say, English resources, it's useful to know what the words correspond to. But let me finish my picture. I have 2 times 0, so I drew that arrow. Let's draw more arrows. You see, for every beginning, for every number, for every congruence class, for every residue class, I will have an arrow that comes out of it. I can always take it times 2. So let's draw more arrows. Let's finish the picture. I already know 0 times 2, 0. What about 1 times 2? Well, 1 times 2, that's easy. That's just 2. Okay? Let's keep going. What is 2 times 2? Mod 11. It's 4. 3 times 2. 3 times 2 is 6 mod 11. So I guess I'll draw it on the outside just to keep the drawing as clean as I can. 4 times 2. 4 times 2 is 8 mod 11. 5 times 2, I already did. It's 10. 6 times 2, now that's 12. 12 mod 11 is 1. So let me continue on upward. 6 times 2 is 12, which is 11. 7 times 2, I already did. It's 3. 8 times 2 is 16. 16 mod 11 is 5. So I'm going to come back around to the 5. 9 times 2 is 18. 18 mod 11 is 7. 10 times 2, 10 times 2 is 20. 20, when I divide by 11, has a remainder of 9. Okay, and I finished my picture. Let's look at this picture. There are a lot of very interesting things about this picture. One of them is that it's symmetric. Do you see? This 1 goes to the 2. Because 1 times 2 is 2. But the 10 goes to the 9. The reason it's symmetric, you see these negative numbers here. The 10 residue class, or congruence class, has lots of numbers in it. Not just 10. It also has 21, but it also has -1. If I take -1 times 2, of course I get -2. What I mean by symmetric, if I drew the picture better, is that all the plus multiplies and all the minus multiplications will be the same. And you can see 2 goes to 4. But of course, minus 2 would go to minus 4. 7 here is minus 4. I'm showing all of this because when you're doing multiplication, mod 11 or mod anything, you can do shortcuts by using the minuses. So I could have immediately known that 10 will go to 9 because 10, I don't like multiplying 10 by 2, but I do like multiplying minus 1 by 2. That's very easy. That's one interesting coincidence. There's another interesting coincidence. Look, everything has one arrow going out, but everything has only one arrow going in. Every single one of these numbers, residue classes, has one arrow in and one arrow out. Always, one in, one out. That would need a proof. We will need to know why that is the case. We'll do that in another lesson. This is just to introduce the picture. But if it is one out, one in, it's like a string. It's like a loop of string. For everything here, there is some string going in and some string going out. This 0, the string is going to itself. But that means this is a very, very big loop in this picture. What's the loop? Let me write it down, and then we will copy it into the next screen. The 0 is special. But then the loop starts 1, then it goes to 2, then to 4, then it goes to 8, then it goes to 5. From 5 I go to 10. From 10 I go to 9. From 9 to 7. 7 goes over to 3. It's not going to fit now. And from 3 I go to 6 and then 1. So it's perfect. 3 goes to 6. And then it goes back to 1. I hit everything in this loop. 0 is just on its own. It's separate. I do want to say, you're not guaranteed that it will be only one loop. It could be many loops. All I guarantee is every single number has one in and one out. And you can imagine many loops of string having this too. Actually, this is 2 loops. One loop is 0, and this is the other. But let me now write that. I want to draw that as a loop. I told you it doesn't matter how I draw these numbers in the circle. I can draw them in another way that makes it easier to see this pattern. So I'm going to remember these numbers and start copying them in a loop. 1, 2, 4, 8, 5, 10. 1, 2, 4, 8, 5, 10. Okay. 9, 7, 3, 6. 9, 7, 3, 6. And the 0 is special, like this. Okay? Remember what my arrows are. In this whole picture, black arrow means times 2. Of course, I said black arrow because I'm about to do something different. First of all, this is very nice. I can have all of them coming around like this. This is telling me lots of very interesting things. With the black alone, I know things like, if I took 2 to the power 4, what is that? Mod 11. Well, 2 to the 4, think about what the arrow does. It starts from 1, and then the arrow is always times 2, times 2. So if I want to do 2 to the 4, I go around 4 times. Times 2, times 2, times 2, times 2, that's 5. Mod 11. What I mean is that these are powers of 2, mod 11. In this cycle, every one of these is what happens with powers of 2 when I go mod 11. As a preview for what you'll see later, how long is this cycle? This thing here has how many numbers? This thing here has 11 of the numbers. 11 residue classes altogether. I mean, between the two. 11 residue classes. But those 11 residue classes, 10 of them are here, 1 of them is there. What that means is that if I took 2 and I multiply it by itself 10 times, then I get back to where I started. This is because the cycle is 10 long. So I do times 2, times 2, times 2, times 2, and I'll get back to 1. Okay. This 0 just tells me that if I start with 0 times 2, nothing happens. To close this picture, to finish talking about this picture, I want to say 10. 10 is not a prime number. What that means is that maybe if I didn't make a times 2 arrow, but I did a times 4 arrow, what would happen? You see, since 10 is 2 times 5, I chose 4 on purpose because that's going to start skipping around. I have 10 numbers in a circle, and now I'm going every 2. What you should see here is that this is going to make not one loop. This big loop is going to break into 2 loops. Times 4, I know times 4 because that's 2 times 2. That's easy. So I can just go bounce to here. Now if I want to take 4 times 4, that's 16. 16 is 5, but I also knew that because it's just 2 twice. And if I keep going, 5 goes to 9, 9 goes to 7, 7, oops, I missed one, just a second. So now I go 7, not to 7. 9 goes to 3, and 3 goes to 1. I have the times 4 is making a 5 loop. And I also, if I start from the 2, 2 times 4 is 8. I'm using a slightly different green, just to show that this still hits all of the numbers exactly once, but breaks the loops into, instead of one big loop and 1 0, 2 medium loops and 1 0. So this is showing that if I did multiply by 4, I still have all of these loops going around, but it's not just one loop. I'm doing this to show you that 2 is special. 2, we say 2 is a primitive root. Modulo 11. This is just what the word is. I want to share the word with you only so that if you read something else and see primitive root, you know what they're talking about. I want to explain the English of the word primitive root. Root. Root is what we usually use to talk about. In English, we use root to talk about things that look like this. This is a square root. But we also write different kinds of roots, like 10th root. We say that 2 is a primitive root, mod 11, because if you think about what 10th root means, 10th root is like what to the 10 is something. 2 is the 10th root of 1. And 10 is the biggest you can have because that's the size of the cycle. So we say 2, this is where the word comes from. Primitive means it has the biggest. To close, why am I always saying biggest is 10? The reason is because no matter what arrows you're drawing, no matter what kinds of arrows of times anything, if you do times anything, I'm making up a times 9. In all these arrows, 0 goes to itself. No matter what, 0 times anything is itself. So the best you can hope for is that the rest of the 10 will do something interesting. But we will talk in another lesson why. What is happening here is that since 11 is prime, these 10 non-zero residue classes will always become some number of loops. These will always become some number of loops. And so the biggest loop you can hope for is 10 with this one else here. This is an introduction to what we call in English modular arithmetic. Which is to say, what happens if I just look at the residue classes and draw these pictures you will discover lots of patterns. I encourage you, if you find number theory interesting, or if you want to know how to do these harder problems in number theory, it's very useful to try to draw a few of these yourself, these multiplication diagrams. You will notice patterns. They will not only help you solve problems, normal problems, but they will also give you more understanding of why all of these number theory facts are true.